we're going to do here is see if we can use calculus to figure out what a graph looks like before we actually graph it. So avoid using a calculator for a little bit. Let's have a little fun with this. All right, so the function that we're going to play with is f of x equals x squared minus x minus 1 over x plus 1. So we're going to look at this rational function. Now, just pre-calculus stuff to think about here for this function. We can look at the denominator and we can see the domain, so that's a good thing to know. So the domain here, x can be anything but -1. So we have negative infinity all the way up to -1, union -1 to infinity. So we can see the domain there. So the denominator tells us, zeros in the denominator tell us undefined values. As long as, undefined values, period. It could be that something cancels in the numerator, so I guess we should try and maybe factor the numerator, see what happens there. That also tells us the zeros. So if we take the numerator, x squared minus x minus 1, and we set it equal to 0, right, that's going to tell us the zeros of f of x. And it looks like that does not factor. Nope. So I would probably complete the square on that, or we could use the quadratic formula. So I'm going to complete the square just for fun, in case you haven't done that in a while. So we bring that 1 over to the other side. We look at that middle coefficient, -1, and we cut it in half. And then we square that number. That gives us 1/4. So we add a 1/4 to each side. Oops. There we go. And then this right here should be the square of x minus 1/2. On the other side, we have 5/4 now. Then we can take the square root of each side. So x minus 1/2 equals the square root of 5/4, which we could clean up. And we, plus or minus, let's not forget that. Add the 1/2 to the other side. So we get plus or minus the square root of 5 over 2, or if we cleaned up the quadratic formula, that would be 1 plus or minus the square root of 5 all over 2. So we have 2 zeros on this thing. We have the domain, so we have some information right away just by our pre-calculus work. Next, we're going to take a look at, see if it has any maxes or mins using the first and second derivative. So let's find the first derivative. Remember here we have the quotient rule, which says take the derivative of the top, 2x minus 1 multiplied by the bottom, x plus 1, and subtract the top, x squared minus x minus 1 times the derivative of the bottom, all over the bottom squared. And we clean that up. So let's see, we got a little distribution to do there, and here we'll have to distribute a -1. So we're going to get in the numerator 2x squared, and then 2x minus x to square. Oops. Better. 2x minus x would be just plus x, and then minus 1. And then here, distributing the negative, we get minus x squared plus x plus 1. And then generally with something like this, we don't multiply out the denominator. We leave it squared. So 2x squared minus x squared means we have an x squared in the top. And we have plus x, we have plus 2x's. And the 1's conveniently go away. And so that's our numerator. So this cleaned up kind of nice. And we could take it one step further by factoring the numerator as x times x plus 2. Now, just some things to note here. Just like -1 was not in the domain of the original function, it is not in the domain of the derivative. So f prime of -1 does not exist. It's not a critical value because f of -1 doesn't exist. So just a little note on that. F prime of -1 does not exist. F of -1 does not exist. So there's no point, oops, no point in even looking at it. It's not a critical point. So the denominator gives us no critical value. So then we look at the numerator. So the numerator here x times x plus 2, if we set that equal to 0, then we get either x equals 0 or x equals -2. And so these are critical values. So now we have to test them to see if they lead to extreme points. It'd be nice to also have the second derivative, because the second derivative test is pretty nice too. And that also tells us about concavity. So let's do that also. So I think I like this form right here, the first derivative, for finding the second derivative. So let's go for it. Exercise for us. All right, so the derivative of that function right there is the derivative of the numerator, which is 2x plus 2 times the denominator, x plus 1 squared, minus the numerator times the derivative of the denominator. So there we're going to have the chain rule because we have an inner function and an outer function. So the outer function is the square. So that means we have 2 times the base. And then the inner function is x plus 1, and the derivative of that is just 1. So I just multiply by 1 according to the chain rule. Not much to do there. And then we square the denominator. So that would be x plus 1 to the 4th power. All right, so then we try to clean this up. And just something to note right away, we have a factor of x plus 1 here and 2 of them there. So I can take out the factor of x plus 1. So I'm not going to distribute yet. I'm going to factor the numerator first, because I see I can pull out an x plus 1. And then maybe I'll make a big green parentheses for what's left. On the top. And let's go back to red here. And in the bottom, I still have the x plus 1 to the 4th power. So let's see, I pulled out one of these x plus 1, so that means I still have one left. So I do have to distribute these two. So that's going to be 2x squared. And then we go up 2x plus 2x. So that's 4x plus 2 minus, let's see, this is gone. So basically I have to distribute a minus 2. So that's going to give me minus 2x squared minus 4x. Did I do that right? Let's rethink that just to make sure. I'm distributing the minus and the 2 through here. So minus 2x squared, 2 times 2 is 4, minus 4x. Yep, that looks good. Okay. This is nice because I get a little bit of cancellation. So this x plus 1 cancels with one of those. So that's now x plus 1 cubed. 2x squared here minus 2x squared goes away. Oh, this is nice. 4x minus 4x goes away. So all that's left in the top is a 2. Well, this came out pretty nice. The second derivative appears to be 2 over x plus 1 cubed. Is that too good to be true? I think that looks right. Anybody say anything funky I did? Okay. So now we begin our analysis with the number line. As far as critical values for this thing right here, this has no critical values. Again, we still have the domain of the function, the second derivative, that x can't be -1, right? So just make a little note. X still can't be -1. That's going to be true forever for any derivative of this function. All right, let's do it. So important numbers at the moment for our number line are critical values from the first derivative, 0 and -2. And then we have this -1 here, which is probably an asymptote. All right, so let's rewrite on another page this, our derivatives without the work, and make our number line. So we started off with f of x equals x squared minus x minus 1 all over x plus 1. And then we get our first derivative, f prime of x is x squared plus 2x over x plus 1 squared. And then we just calculated our second derivative, which is going to tell us about max and mins and concavity. And the second derivative is 2 over x plus 1 cubed. This one gave us critical values, so we're going to look in a number line. Red, and they were, let's see, 0 and negative 2. So let's put 0 over here, oops, 0 over there, and then negative 2 can go somewhere over here. Negative 1 is in the middle here. Oops, it's not 1. And that one's a problem, right? So we can't actually plug in negative 1. I'm going to put an open circle there. And then we're wondering if there's any change on each side of these critical values. Do they turn into extreme values? So we have to pick numbers on each side of these guys here for now. So like maybe we'll plug in negative 3 over here. And in here, we can't plug in negative 1, so we have to plug in something like maybe negative 1.5 or negative 1/2. Let me put this in because I might want to check it later. And then over here, we could do 1. That's a beautiful number. So I guess we could start there. What is f prime of 1? Now really, I only care about the sign of that. The actual value is not all that important at the moment. But that's not hard to calculate. 1 squared minus 1 is 0. In the bottom, I have a 2, so I get negative 1 over 2. So I think this is negative 1/2. The important part that it's negative, which means the function is decreasing. If I did that right. So did I do that right? Oh, I plugged it into the wrong spot. I plugged it into f of x. Over here, Gary. It is not decreasing there. Oh, dude. If we plug in 1 here, well, everything's positive, so I'm going to get a positive answer, which is what? 3 over 4. Positive, which means we are increasing in this interval. And then if we go over here, and we could also jump ahead to the second derivative, like if we plug in 0 into the second derivative, we did this at the end of class yesterday, that tells us the concavity at 0. So if we plug in 0 here, we get 2 over 1. That's positive. That means concave up. So through 0, it's concave up. Now concave up could be that right there. It could be just part of that, right? So it's something like that right there. All right. So we know it's concave up there. We might as well check the sign over here. If we plug in a negative, so I'm going to go with f prime of negative 1/2. So 1/2 squared is 1/4. That's positive. And then 1/2 times 2 is 1, but it's negative, so minus 1. So the numerator is negative. The denominator is squared, so it's positive. So I'm getting a negative answer here. Negative 1/2 plus 1 is positive 1/2. Squared is a 4th. I really don't need the exact value. I just need to know that it's negative. Oops, 1/4 minus 1 is negative. So it is decreasing, which means we have this part of concave up, not just half of a concave up, like dish kind of thing. All right, so moving over here, let's check the second derivative at negative 2. So with the second derivative, we actually test the critical points. With the first derivative, we test each side. I usually like to do both to be clear. So second derivative, plug in negative 2. We are cubing a negative number, right? Negative 2 plus 1 is negative 1, so that stays negative, so that is negative 2. That negative tells me this is concave down. And so it's either like this, or maybe just part of it like that, or like that. And it kind of depends on what happens on the other side here. So the first derivative is helpful too. So we're going to try 3. So first derivative at -3, that's going to give us +9 minus 6 over a square. -3 minus -3 plus 1 is -2, squared is 4. So that is positive. That means we are increasing in this interval. And so we have this full concave down shape there. All right, we're making progress. Notice that around, let's see if I want to show this, highlighter maybe. So remember, the function is undefined at -1. The derivative is undefined at -1. The second derivative is undefined at -1. But I'm going to split this right there just because I want to point out that the second derivative is negative on one side of that undefined value and positive on the other. So we don't have an inflection point because the function doesn't exist there, but we clearly have a change in concavity. It's concave down on one side, concave up on the other side. Now we need some numbers for the graph. All right, so then I want to know what is f of -2, because that's going to be some kind of max, local or absolute. So what is f of -2? And so if we plug that in up here, what do we get? We get 4 plus 2 minus 1 over -2 plus 1 is -1. So that's 6, that's 5, -5. So that means this graph has the point -2, -5. This point is some kind of max because it's in a concave down region of the graph. And so the max is y equals -5. All right, other side, if we plug in 0, what is f of 0? So that one's easier. F of 0 is -1 over 1, which is -1. And that's in a concave down section. So we have the point -0, sorry, -1, and that is a min. Now, the extreme point, right? But the min is the -1, not the 0. 0 gets us there. So y equals -1 is a minimum for this function. All right, so I'm just going to make kind of a rough sketch here, try to figure out what's going on. And then we also had those zeros we calculated earlier. What was that? The zeros were 1/2 plus or minus the square root of 5 over 2. Square root of 5 is 2 point something divided by 2. So I can't estimate that in my head right now. That's okay. We'll plug that into a regular calculator. But let's rough sketch this. Squeeze it in over here. All right, and then 1, 2, 4, -2, -4, 2, 4, -2, -4. All right, so what do we know? Let's plot some points. Let's stick with green. We have a max at -2, -5. So -2, -5 is over here. And so then the function somehow has a max there. I don't exactly know how it curves away from that, but it does something like that. And then at 0, -1, so 0, -1, we have a min. So it does something like that over there. We have an asymptote at x equals -1, because nothing cancels with the numerator. So I'm going to draw that in as a dotted line. Does this function have other asymptotes? So for sure, I can draw part of this. This is going to rise up toward that somehow. And then that 0 is related to, I guess, the -1 here. And then there's going to be a 0 on the other side, which is the positive version of this. So let's see, let's just guess at that. That's a little bigger than 1 plus a half is going to be a little bigger than 1.5. So it's going to be like over here-ish. And this, again, square root of 5 is a little bigger than 2. Divided by 2, it's a little bigger than 1. And then to take a half from that, so it's going to be a little more to the left of -1/2. And that looks reasonable on my graph. And then this side plunges down. But the question is, what happens out here and here? So to think about that, we have to kind of think about what happens as x heads out to infinity or -infinity. So I'm just going to go think about this for a second. And do you remember your rules about asymptotes of rational functions? Way back from pre-calculus. Let's see. So you would have a horizontal asymptote if the degree of the numerator matches the degree of the denominator, but the degree at the top is bigger. If the degree of the top is 1 bigger than the bottom, you get what's called a slant or oblique asymptote. And to find that slant asymptote, you just do long division on that. We could do synthetic division too. What do you want to do, long division or synthetic division on that sucker? You could do either one here. Evan votes for synthetic. Go Evan. Okay, so with synthetic division, we think about what x value makes the denominator 0. So that would be x equals -1. So then we take -1 into the coefficients of the numerator. 1 minus 1 minus 1. And then with synthetic division, the first coefficient just comes down. -1 times 1 is -1. And then you add those two together. So that's -2. And then -1 times -2 is +2. And then we add coming down, that gives me a 1. So that's the remainder. So to interpret this thing right here, what that means is that if we take x squared minus x minus 1, divide by x plus 1, then x plus 1 goes into the top, x minus 2 times, that's this part, with a remainder of 1 over x plus 1, the original denominator. And if we think about this right here as, say, x goes to infinity, what's going to happen is that this fractional part is going to go to 0, and this linear part dominates. Meaning if we zoom out, then f of x is going to look like, because this is getting smaller and smaller and smaller, it's going to look like x minus 2. So x minus 2 is our slant asymptote. So let's graph that in there. Isn't this exciting? I love this part. So here's, let's see, x minus 2. So from -2, we just go up 1 over 1. So it goes through here like this, and then down this way. Can a function cross a slant asymptote? The answer is yes, it can. I doubt this one does. And so I'm thinking it's just going to stay underneath like that, cutting in tight there. And then over here, it's going to head closer and closer to that like that. Hey, we did it. We made the graph. Let's see if we did it right. All right, so hopefully you did the whole surprise thing with me here and just analyzed it. Let's see if we got the right graph. So let's whip out, say, Desmos today. Oop, where'd you go, Desmos? There you are. See how we did. F of x is a fraction, x squared minus x minus 1 divided by x plus 1. Okay. And then let's zoom out just a little bit. That looks pretty good. Let's graph the two asymptotes. X equals -1. Nice. And the other asymptote we believe is y equals x minus 2. Nice. Look at that. And then if I click back here, Desmos very kindly says, hey, you've got a minimum here and some zeros here and here, like we predicted. Let's double check we got those two right. So one of them was 1/2 minus the square root of 5 over 2. Yep, that's the other one. And then, right, if I go back here, that's this one right here. And then if we switch to a plus, 1.618, Hey, isn't that the golden mean? Oh my gosh, this thing has the golden mean as one of its zeros. That is so cool. I didn't mean for that to happen, but it did. Sweet. We did a good job there. Isn't that fun? I love doing this thing. All right, let's try another one. How about, let's see, we could do a trig function or another funky radicalish function. Let's do, I think we have time for both. Let's do a funky radicalish function. All right. New example.